that many. So I actually came to Skills Matter 3 years ago on a holiday and came to a functional programming thing, which is a bit mad. The last year I've been in Glasgow, though, working on a mixture of things, but quite a bit of Clojure. And this is not necessarily about that project, but it's related. So pragmatic means I can talk about whatever I care about. There's a lot of aspects to performance testing. I'm mainly focusing on the sort of things that we've been doing, which is businessy web apps with a business focus. So if you want to know how to tune your, core CPU behavior, I won't cover that. So, how many people know this guy? This is Noose. He's got a famous quote that people keep on mentioning, at least I keep hearing it. Premature optimization is the root of all evil. It's actually a little bit more than that. What he actually said in the original thing was that 97% of the time, premature optimization is the root of all evil. We should still remember that other 3%. So, that's a good quote. There are lots of other quotes that I've heard quite often, and I've said some of these. One of them is, we don't have that many users. Performance, we don't really have to care about it. And then there's, we're using Mongo. Mongo's amazingly fast. We don't have to care about the performance of Mongo, it'll be awesome. And then there's, we don't really have time. Performance, we find, we'll worry about it near the end. We'll worry about it when we go live. And we're using Clojure. It's on the JVM. It's fast. It's faster than Ruby, so it should be fine. And then there's this one as well, which is, Clojure might not be fast enough. Let's put some type hints in. And that is premature optimization. There's all sorts of things people think about. Maybe I'll put some transients and some multi-methods and some inlining and a whole lot of other stuff. But that's the definition of premature, is when you say, maybe this. So this is a true story about actually a few projects. But rather than talk about the real bits, I'm going to talk about cute animals. So let's go and start app. The screen changes. Oh, yeah. I love this app. This is called, what's it called again? Cathode. It's the best terminal emulator ever. You can actually theme it, so we can say, let's go for a 1986 TV. It's just magical. This really takes me back. Oh, sorry. Yeah, it's a little bit. I think there is a degauss function somewhere. Yeah. And as is the case with all real demos, it's failing. What the hell? Wrong number of args. I don't believe that. Wrong number of args passed to main. Oh. Let's just try running it without the ring magic. Never tweak the code before a demo. That's probably the answer. Okay. So here's our app. Cute animals. We love cute animals. Tumblr is amazingly full of cute animals. It's actually quite scary. There are a lot of cute animals out there. And Tumblr has this great API where you can just say, get me this. Show me all the cute animals. You can even look by tags. You can say, show me all the ones that are tagged with puppies. We love puppies. Lots of puppies. Or adorable. Yay. So this looks okay. This seems to perform okay. If you actually load it up, it's not performing all that okay. So I'll just go back to my presentation, given I'm not able to do live changes. So, cute animals. So we built something like a cute animals site, and we followed the classic performance testing approach. We built the whole thing, we got it pretty well ready to go, and then we decided to test it. We didn't use, so I'm using JMeter. JMeter is pretty ugly and horrible, but it is also free and works on Java. There are lots of better tools out there. Locust is meant to be really awesome, but JMeter is reasonably straightforward. So if we look at our app, I've got a few things. I've got an index page. I've got some puppy GIFs and all of the different bits and pieces. If I run the app and have a look at our response time, if it runs, live demos. So we can see these are our response times, and they're pretty horrible. We're getting 14 seconds, 16 seconds. This is milliseconds. Sorry about JMeter being horrible for display. So once you have a number of threads and a number of people hitting the server, it just gets pretty rotten. So this is our classic approach. Screen reload. I'd be better off with the console. Hello, screen. The other problem with performance testing on a laptop is that it kills it. So we build it, and then we test it, and then the screen goes blank. Eventually it'll say, and then we panic. Hey, then panic. I'm going to go back to display and see if it fixes itself. I'm going to do slightly less live demos. So we have this performance curve that we saw, which was pretty horrible. That's what happened testing. We were getting 16, 20, this is my cute animals thing on a laptop, 24-second responses. And that's for a page that really just shows you a list of the animal names. And this is a pretty bit of a nightmare to test. So the first step of testing is to try something simpler. So I've got a fast and a slow URL. You can see pretty straightforward. Fast does nothing. Slow says, let's sleep for a bit, and then test it. And this is what JMeter comes out from this. This says slow, starts off at about 160 milliseconds, and then it gets horrible. Now this is ramping up the number of users. So we start with no users, we're going up to 100 users, and it starts getting horrible. And actually, that's quite painful even for a really simple thing, that obviously it's not taking 100 plus a random number of 100 milliseconds, it's taking a lot longer. So the next step about testing this sort of thing is to instrument and measure. So it's really important to be able to measure your system behavior. So we're using Graphite. There are lots of other tools out there. There's one called Ryman I've heard of. Graphite's a good basic one. We're already using that for Java apps. So Graphite lets you do a whole lot of measurement and saying, what are our performance like? So in this case, you probably can't see it on this screen, but actually Graphite was saying, really it is only taking 150 milliseconds. There isn't, this display you're seeing, this time you're seeing is not in the app, it's actually somewhere else. So what we did for this one is to worry about thread pools. So if you look at, my slides seem to be in a weird order, doesn't matter. So give me a second. I've lost the slide. I have no idea why. Anyhow, the core problem here is that thread pools are, by default, Jetty has a thread pool limit. It says, oh, we're only going to allow 50 threads. In my app, we had 100 threads. Once you get to 100, it starts saying, oh, you've got too many threads. There's not enough threads. I'm just going to queue up your requests. So probably where I'm going to find out where that thing is. So max threads, you set max threads up higher, in your Jetty handler, and it will go, oh yeah, that's fine. So the key lesson is that you've got to deal with pools. There's a lot of things in the system that have pools that have to be tweaked, and you need to read the manuals and say what will actually happen. So if we up the thread pools, we still get a slower response on a laptop, but it's nowhere near as bad, and nowhere near as bad for dealing with threads. So it's a quick example of how we use this. It's a scientific method. You build a hypothesis. You say, maybe we've got a pool limit problem. You test it using something like JMeter or another tool. You fix it, you update the thread pools, and then you repeat. And that's where that somewhat better slide should have been. To say our performance is now pretty flat. It still gets a bit higher as we go further on. And there's lots of things you can monitor. So there's a lot of tools. We're using Graphite and StatsD, and there's Ryman, and there's a whole pile of other tools that we'll measure. And it's important to know there's no point having a performance test failure and going, I have no idea what's going on. So you can measure your server, your JVM, your application. Key things that we wanted to measure are our endpoints. So where a HTTP endpoint comes in, our external interfaces where there's a database, external call, and anything else that might be slow. So we're using Composure. And so this is a way of just using the Clojure metrics library to say I want to measure these things. So I've got a default route. I had a timer that says index page. We time it with a timer called index page. I've got a timer on the hosts page. Each of these I've individually tagged. So I can actually show you in... how did that guy get there? Nothing to do with this talk. So in Graphite, those functions turn into a whole lot of timed things. So I've got all the different API points, the index page, the all page show up in here, and then you can pretty simply say, yeah, give me a graph of the mean response time for that thing, and show me in the last 5 minutes. And because I killed the performance test, there's nothing much there, but yeah, it's really great for building up these sort of real-time graphs and saying what went wrong where. So we build these timing threads. We set individual timing, but you've got a lot of endpoints in a typical app, and we said, oh, maybe we can build a macro to hook into Composure to try and time all of the endpoints. Macros are a nightmare. They're awesome, they're wonderful. Everyone who uses Clojure should know how to do macros, but they're all compile time behavior, and compile time behavior gets really messy. You can't profile something that's inside a macro because it doesn't exist at runtime. And some macros, so we wanted to get into Composure roots. This is a macro that we found that was in libnoir for doing similar things to what we wanted to do, putting security roots in your Composure roots. It goes through the tree of your Composure endpoints. It inserts a restricted call around each of your endpoints, and we thought, hey, we can do this. And we actually built a working version of this for timing every endpoint, but it had some really bizarre behavior, and it was sheer madness. And no offense to the author, but we should have used BIDI. The trouble with Composure for this is that because it's all macros, diagnosing, I think we spent days trying to get a thing, and then we found that actually this macro and our timing macro fought with each other. This macro does some lazy behavior in its restricted roots, and so did our timing macro, and we ended up having timing metrics that were tiny because something somewhere lazy leaked out of our thing, so beware. We also wanted to instrument a whole lot of other functions in the system, things we thought might be slow. And we used this wonderful library called Robert Hooke. People don't know Robert Hooke. He's this guy. He was all over the UK. I saw his picture, this picture actually at King's College in Cambridge a few weeks ago. He loved measuring. He worked in telescopes and a whole lot of geographical things. He's actually involved in the Great Fire of London. After the Great Fire of London, he did a whole lot of measurement of buildings burnt and reconstruction, which fits a lot into our performance testing because we had lots of great fires, and having a guy who was into measuring fires was a good thing. There's a library called Robert Hooke that basically, if people haven't seen it, it lets you at runtime instrument functions and add behavior to them. So this is from their demo. You can say I've got an examine function and I've got a microscope function that decorates that examine function by converting its parameters to uppercase. And you can just say add hook, and then when you call your examine function, it will also call this microscope function. So we wrote a little bit of code. This is not a library you can download, but it's pretty simple to recreate. That says, using the metrics Clojure library for timing, add a hook to any function to time it. I'm not going to go into exactly how this works. So we can then say instrument with timer and say, okay, let's choose our functions that are slow and turn on instrumentation for each of those functions. This is good, except it has one slight problem about laziness. This will wrap your function in a timer, but some of these functions like the find validated and the posts by tag, they're inherently lazy. Clojure laziness is wonderful for performance, but when you're trying to measure something, you want to say start a timer when this starts and hit a time when it ends, then that doesn't work. So you can actually turn off some level of laziness. There's a function post walk. It's not really designed for this, but you can say post walk for any Clojure data structure, and it will apply a function to the contents of that data structure. If you say post walk identity on a data structure, if it's a map, it will go through the map recursively. If it's an array, it'll go through the array as sequence. And that is a way of hackily turning off laziness. So you can make a version of our time talk function that says after you apply everything else, just kill laziness. It will actually make the performance an awful lot worse because suddenly you're realizing all your functions into memory, but it also means that your functions are actually timeable. You really know how long they're going to take to start and finish. So we did this. We fixed this piece of code. We fixed our Jetty pools. There are lots of other pools in a production app. JDBC connection pools are a thing. If you're using memoizing and caching, then there will be pools in all of those things. There'll be timeouts of all those things. Database caches in general are something you need to track. So fixing all those things, this system got a lot better, but it's still quite slow. This is again on a laptop, but the adorable scale is a little slow. That's 4 seconds. The puppies is a bit faster. The index page, which just shows a bunch of text. I'll go back to the index page. Look, you can see it loading. It's just showing a whole lot of tags and a whole lot of URLs. There's nothing there. That should not take as long to run. Mind you, this is, we check the metrics for this thing. This is their metrics to show the index page going way up to 62 seconds from Graphite. Our other functions that the index page calls are actually pretty quick. So this is where you start saying we'll turn off laziness to see what happens. Unfortunately, you turn off laziness and it goes up to 125, 150 seconds, and the whole testing is kind of pointless. So trying to test this sort of thing at this scale when you don't know what's going on can be a painful experience. So a main thing to do here is to simplify things. Even with one user, this is slow. We don't really need JMeter to test this. JMeter is this amazingly powerful, and there's other test tools that can test thousands of threads. But actually on one user, that's pretty crap. That's over a second to load the page. Even these ones, they're okay, 200 milliseconds, but they're doing almost nothing. So at that point, we and investigated the code. So, sorry, the colors are a bit vague. So our actual index page does this find validated thing to say, get stuff from the database, and it's always taking a prismatic schema in there and saying, I want to validate this data against prismatic schema. And that find validated gets from the database and then says, oh, non-lazy, validate all the results. So prismatic schema, I don't know how many people have used it. It's a great way to do schema checking, to check the validity of data structures. It's good for APIs and the like. But we did some timing on this, like simple validate a schema. The schema is reasonably complicated, but not horribly complicated. And it takes 1.3 milliseconds to validate a single object. 1.3 milliseconds sounds really fast to me. It sounds like not a lot. It's worth thinking about real times, though. This is a great scale of this. If you consider one CPU cycle to be 1 second, then memory access takes about 6 minutes if you scale everything proportionally. Hard disk I/O takes 1 to 12 months. Internet to Australia takes about 20 years, which is probably realistic. And packet retransmit when your packet connection fails is about 100 years. So in terms of those scales, schema validate 1.3 milliseconds, that's about 1.6 months. It's a huge amount of time relative to your actual CPU cycles. It's doing a lot of work in there. And the real trouble here is we're doing it maybe 1,000 times. We're showing a whole lot of stuff on a page. So that turns into 1.3 seconds. So it might not be too slow if you just had to do it once. It's fine for an API call. 1 millisecond overhead on an API call is fine. But if you're repeatedly doing something over and over again, then you really don't want to do that 1,000 times. Similarly, we're using find maps in Mongo. Find maps pulls a map of data out of a pulls a Mongo object out of a database and converts it into a map. It's 40 microseconds. It's not too bad. But if you do it for 1,000 things, then it's quite a bit. It's interesting, though. We're only using that find maps to get a single field. I won't tab to the code because it will make the screen die again. So we're just getting a single. We really only care about the title and the URL of the page. If we cut find maps down to just 3 fields, suddenly instead of 40 microseconds, it takes 400 nanoseconds. The work is that we're getting the entire database object out of the database, and then we're throwing away 95% of it and just saying we need these 3 fields. So the key lesson we got out of this type of code is to say, if you're doing something 1,000 times, don't do something slow. Don't do a schema analysis when you've got, you already know what the data is like. You wrote it to the database. You could be pretty sure it matches your schema. Don't use the fields you need. And possibly paginate. Maybe 1,000 things is too many. Maybe you should show 100 and then say next and previous things. But test it first. This is the theme here. Test it first, because maybe 1,000 is fine if you tweak the other things, and you wouldn't want to upset Nooth on this sort of thing. One of the things in that thing is that tags list. So the tags at the top, these are generated from our database, but they really don't change very often. If we want the cat tag, it's always the same. There's always a cat tag. They might change really occasionally. So the other key benefit we got, especially in our live app, is you can memorize things. Memoizing is awesome. If we say memorize our tags, and there's a core.cache gives you more control. You can memorize with a time limit. You can memorize with particular cache sizes. But this drops our thing. So the first time you hit the page, you get 450 milliseconds, and then it goes bam. I don't need to care anymore. So this is the end result of taking out schema, taking out the tags, only getting a small amount of data from the database, and suddenly our index page comes back in no time at all. It's like 5 milliseconds or something. That's kind of what you'd hope. The next problem, which I couldn't really show here, is about database indexes. Now, this is a thing that seems to happen over and over. This is not a Clojure problem, but it's happened on multiple projects. People don't think about database indexes. Mongo indexes, Oracle indexes, Postgres, whatever database you're using. Every database has a way to say, I'm querying by this non-key field, and people keep on writing stuff that just doesn't work. The only case you should do a query without an index is if it's completely ad hoc and you're a tester or somebody and you want to query it as you go. MongoDB has a problem of being too fast. I can't really demonstrate this on my local laptop because even without an index, I can pull back any sizable database in milliseconds. But definitely on significant databases, indexes kill you. We also discovered this really handy setting in Mongo. If you run this command on Mongo, anytime you make a query without an index, it returns an error. It says, no, you're doing a table scan, I'll just die. So it makes diagnosing these things really useful. You don't want to turn it on in a system that anybody's going to use for anything else, but it's extremely handy. The other thing you see somewhat, and this is a functional programming problem to some extent, is people love using map. People might say, oh, I've got all my tumblers and I want to map a partial, I'll get all the posts in the tumbler, and then I want to map all the pictures for the post. And that's going to say, oh, I'll get 1,000 tumblers, and then I'm going to get 10 posts each, so that'll do another 1,000 queries to my database and get 10,000 results. And that's going to do 10,000 queries to my database, and the cost of this is just insane. It's really tempting when you already have these functions in the system, and you're thinking in code, and you're thinking maps and the good behavior. SQL can do this for free. And just using join. You'd think people wouldn't think of this, but I've seen it all too often in code. So we get a bit further into this, and we've still got some slow pages. That adorable page is still taking a long time to load. And there comes a point where you're getting this to say, I need to know what's actually happening inside the JVM. You can do timing. You can roll your own profiling, and that can get you a certain way. There are good things. JVisualVM comes for free with Java. It's a bit limited, but you can get a lot of metrics about that. YourKit is awesome. It's commercial. You can get a 15-day trial license for free, or if you're on an open source project and you can prove it, then you can get it for free for that project. And in terms of YourKit, it just makes it wonderful to say, I've got my app. I can attach to my app. I'm not going to show this, but you can attach the app and you can get a thread trace and you can say start sampling, sample the app under a load, under a single load, and get breakdowns of exactly where the time is spent. So this is a breakdown of my puppy app. So in YourKit, I can see that I've got my web roots and it calls, you get enormous stack traces in Clojure, so it's a bit of a headache, but you can usually trace them back to code. So my handler calls the timing macro from the metrics library, which calls my web roots, which calls my tag page, which calls stencil render. So stencil is a nice library for rendering HTML or other stencils from objects, and that's what I'm using to generate those pages. And then it gets into lazy sequence land and gets a little bit mad. But we know there's something in the render file. So this is the code, I'm sure it's spelled at the bottom of the screen, the code that actually loads a page. It says DV posts by tag to get the posts, and the post summary to get a summary, and then calls this render file. This is the other way you can remove laziness is you just put do all in. And as people said before, it will make things horrible, but at least you can measure how long this function takes and how long this function takes and how long this function takes as separate units of work. So once we remove laziness in here, we still have the render file somewhere in here. So we pull down, we get our summary, but then we have this, if you look at the percentage of time, a whole lot of time is spent just doing nothing. These are all the same time. But right down here, we've got this render string that's taking most of the time. The actual render under that is taking 1% of the time. The render string function that we're calling takes 22% of the time. This is out of about 25% actually spent processing. So most of the time is in this rendering. So this is the code I'm using. Quick quiz, anybody would have any ideas what could be wrong with this piece of code? Not memorizing. Well done. It's not memorizing the passing string. So render string, if you read the manual, which we didn't do in time, if you actually read on the front page of the stencil library, it says render string doesn't cache anything. It doesn't memorize anything. It doesn't it just reparses this string every single time. If we replace that render string with render file, sounds slower. Instinctively we said, oh, rendering files would be much slower than strings. Then the files are all cached, and their parsing is cached, and it just reruns the thing. We got this wrong several times. We tried not using a string inside a template, using lambdas in our mustache, stencils, doing a whole lot of other stuff, and it just doesn't work. Render string, use render file, and suddenly our performance, we've got that one spike from our building our tags, and then our performance is now down awesome for everything. This is still one user, though. So on my laptop under load, I'm still getting 3-second, 4-second response times. You still will get to a point where your load gets heavy, but there's a point where you just say, look, it doesn't matter. This is a laptop. I shouldn't be testing on a laptop. Let's put this on more than one server. Let's put it on a server with some more CPU. This is the point where some people might say, oh, I'm going to tweak further. I'm going to go and do, type hints and the other sort of thing. But it's not necessary for us. That was enough optimization to make the thing perform well enough under the actual users we're expecting. Other things that we had, actually this was not something we had to prove by testing, but if you know something is going to be slow, the other thing is not everything has to be real time. You can queue up things. You can say, we're going to put a queue in, we'll send our work to the queue, we'll deal with it asynchronously, another server can handle the load, we'll just get our data back when we're done. And then there's a last resort. If you really have to, you can go and tweak Clojure. This is quite a good book. Clojure HighPerformance Programming, it digs into a lot of the details about the JVM and tweaking Clojure. It does make Nuth a little bit angry in my mind. It has an awful lot of, it sort of jumps straight into, hey, you could do this thing with like state and transients and other things that you probably don't need, depending on what you're building. If you're building a music system, you might need some of those things. So I haven't talked at all about browser speed. Browser speed is a whole different issue. We do have a whole system that is JavaScript heavy, client-side browser system. I'm not going to go into a lot of detail of it. It's quite a different world. Most of those things matter more about the individual user's performance. One thing we have been doing is to say we'll run the system under load, we'll run a performance test against the back-end system, and then we'll run a user on a browser using our normal web automation, using WebDriver tests, and we'll see how the performance of that single user is when the server is under heavy load and has a whole lot of data. There are also big-scale projects. If you've got a big-scale project, there are tools out there to do cloud-based browsers. But we got good enough speed out of these tweaks. So what could we have done better? What do I feel went wrong? Well, a lot of our problem was we did all this right at the last minute. A lot of our pain was we were doing all this stuff right, as we were saying, oh, are we going to go live or not? Let's performance test it. And we had all these headaches. So there's a lot of options you can do when you're testing. People tend to go straight for the right-hand side. They tend to go, oh, we'll have realistic behavior. If you can get it, production data, we'll get real browsers, we'll get full hardware. So the left-hand side of this scale, these are all things that are cheap and easy. If you've got one user, you're mocking your browser in memory, you're using ring mock or something, you're testing things locally, that's really easy and it's flexible. As your code changes, your tests will change. It's straightforward. This sort of full scale, I'm going to run Load Runner or some other huge tool and run the whole thing, is hard, it's slow. As your code changes, your tests will break. Unfortunately, this is what we always seem to end up doing. So these are the things that went wrong for us. We had pool sizes, we had looping over slow data, we had not memoizing things, we had database usage, stencil. 97% maybe of our problems would have been solved if we just tested with one user, with simple repetition, with realistic data. So this is a key lesson that we learned. Realistic data is not that hard. We knew roughly how many users, we knew roughly what our production systems were going to be. If we had simulated real production data on day 1 or day 10, we would have found most of our problems just by seeing them and saying, oh, heck, the home page is really slow. And otherwise, the fast test, if we did these things in a normal unit testing framework, but pointing at solid data loads, most of our problems would have been sorted. We wouldn't have had nearly the same sort of headache. This relates, to my mind, to the test pyramid. I don't know how many people are familiar with the test pyramid. Normally in testing we say we do a small amount of end-to-end UI tests. They're slow, they're painful. We do some of them so we know the system works. We do more integration tests, and we do mostly unit tests because unit tests are fast. Unit tests will actually find our problems right at the start. And so I'm moving towards saying we should have the same thing for performance testing. You have a single user test. You probably should have a lot of data, but you keep your tests simple and you put them in your tests that run on every build and run every time you make a change. And then you can graph those changes and you can say, hey, today's tests took 2 milliseconds and yesterday they took 1 millisecond, and start tracking your performance over time. And then have a few production-like tests. There are still things that are not realistic. You still need to try something against your load balancers in a multi-zoned architecture where things are like your production world and know what they're really going to behave like. But less and less of these and more of these. And Nuth's phrase about about premature optimization. So we work with a continuous delivery mindset. This is something we're trying to encourage. We're not always very good at it, but our ethos is to say we should be able to deliver weekly. We should be able to push into production all the time. And building a big test phase at the end doesn't work with that. We want to be able to say, hey, this change is not risky. We want to be able to say, this thing can work. So testing your performance is a way of getting around that premature optimizations. It's not premature. if you're actually saying, hey, this thing is slow, I need to fix it now. So if you're continually testing and you're continually scientifically test driving things, then hopefully your tests will be in the critical 3%. So I'll do a quick demo while this thing is going. I don't know why my line run's not working. I might have to find out why. Let's try line run server. Line ring server, that's the problem. Nobody pointed that out to me. I don't know if degaussing the monitor actually speeds this up or not, improves the quality or not. But I was going to do more demos as I went along, but because of the slide transition, it's a bit painful. So if I load my main page here, you can see it loading. It's taking a while. It takes quite a while to get individual pages. I actually have an offline mode which speeds that up somewhat. Just give me a second. Which just uses a local server to load local images. Yeah, it's not refreshed yet. Offline true. There we go. Local images. So that now performs without the browser overhead of loading images. So, but you can still see even with no images, it's quite slow. But I've got now tags. So this is turning off schema validation and using a full database query and memoizing those tags and string rendering. And now, if I load the page, and I let the thing recognize it's really fast. All these things are now lightning fast. So that's pretty well. So that's pretty well it for me. Any questions? I'm happy to show more of the code too if people want to see it. I got this guy. Those are all the different links that I talked about. Yeah? Tend to run. Okay, the question is when we're automating our tests, do we get the system to fail outside our thresholds or do we keep going? We do both. So usually for the automation we don't get it to fail. Usually for the automation we just want to know how long it takes. Manual testing, we will then say, okay, we'll do a break test. We'll see how high we can get it to go. But a lot of the automation is about early feedback and fast feedback and saying, I want to know, has it got slower, but not what happens if it breaks. Testing breaking automatically is quite hard. Oh, breaking the builds. Yes, the build should break, so you should set a threshold. That's how you know that it's broken. So yeah, if you might set it fairly high, but you say, if it's getting above a certain level. I've seen people with ratchets as well where they track the build and they say if it's gotten significantly worse than the last build, then it should break, but that's more work. Yeah? Yeah, we've got automation for pretty well all of our deployments. So we're using Chef to build our systems, and that is a big thing to try and aim for is repeatability so you can build your systems for testing. At our most recent project, there's still a lot of manual steps, but I have worked at a place where everything was on Amazon, and so to run a suite, there was a command that span up a brand new production-like system and then tested that. But not for the... Yeah. So when we do automation, there's every build test. There's also every week tests, and every week tests on the current thing I'm working on. Every week we generate a full database and run a slower test where we can. Sounds like a good idea, but no idea. Versions where we do record and replay, but the record and replay, it's very hard to do that in the sort of environments we're in a good way. But if you had real, like, I'm still talking here about business loads, so I'm talking 10,000 user levels. Some of those sort of tests, if you're building a real, like, public-facing website, you'll have to do more of that sort of behavior. Sandy? That's very true. In the real world, when we've done this, we did memorize some things and then unmemorize them again later when we've solved the underlying problem. Memorization is, and even just using a cache is a bit of a cheat, because it also means the very first person to hit your system still gets the horrible behavior. And if you change the thing, if you change the tags, then somebody somewhere gets a really slow response. So yes, you have, it's a quick fix. If you really know it's never going to change, memorization is reasonable, but yeah, definitely. I'd say partly, yes, but I don't know how many developers are actually really good at reading manuals. I mean, we say it all the time, but it's been a buzzword for about 20 years to say RTFM. This is true. Well, this is part of my point. We shouldn't have. We should have put in stencil, and then somebody changed it to do a string and suddenly seen our performance drop in our unit tests or in our daily performance run. We shouldn't have to spin up JMeter to see that. You should be able to test these things early. And I am trying to avoid the other problem of if you tweak every, stencil's a bad example for that, because that, it should have been genuinely read the manual. But if you spend forever trying to tweak everything, it might not matter. Your performance might be fine without. String stencils are fine if you're doing a single page. You just don't want to repeat them 10,000 times on a page. So it's a big it depends thing. But I agree, reading manuals is something that it's a bit of a plague, especially for teams under pressure and trying to deliver stuff in a hurry with a project manager looking down their backs. So it is a cultural problem. Yeah.
What do you do when your performance?
So we have had, well, not in this project, but I've had previously to fall back to Java. So that doesn't help with the JVM itself. It comes back a bit to what was said earlier about maybe using Erlang. If you've really got something where the JVM is not fast enough, is that what you're asking?
Yeah, like integer parsing in the JVM up until version 8 had a global lock.
Yeah.
So what do you do when you hit stuff like that? Do you go and try to push through JSR, or do you just throw up your hands and say, screw it, we'll happen now?
I throw up my hands and say, screw it. We should push that sort of thing through. But yeah, quite often, especially in a business context, part of the problem is getting somebody to pay for doing it properly. The business, it's quite hard to actually, one of the issues that I would say about this, it's hard to estimate how much time you should put into performance testing and going to a business stakeholder and saying, we want to spend 2 weeks at the end of the project testing. They're used to that, and they'll say, yes, if you say we want to spend a story per week improving this stuff, then it's harder because they don't quite get that. So yeah, telling them we want to fix the JVM, that's really hard. And hopefully there is a library somewhere that we can steal to do the work. Okay, no more questions? We can have lunch. Thank you.